Hello and welcome to the Star Sailor podcast, Questions of a Stellar Nature Part 2. This is the second part of the interview we had with Dr. Robert Simpson for 365 Days of Astronomy and released here as we couldn't fit it in.
And moving on from star formation and star existence, shall we say, on to star death. The supernova remnant SN 1987A, which I'm sure some of you recognise as the Galaxy Zoo logo, there is no detectable collapsar remnant within it. Collapsar remnant being white dwarf, neutron star, or a black hole. And it's raised a few eyebrows because there's suggestions that it could maybe have created a quark star that's dull that we can't detect, and therefore we discovered a new type of exotic matter star. Either that, or it's still obscured by dust and we can't see it. So do you have any ideas on the...
Oh, well, okay, so I was saying earlier about the areas of astronomy and things that I like. Well, quark stars is one of those areas that, I don't know much about it, but I like to read about these sorts of things. So a neutron star, just to clarify for anyone who's not sure, is a star made of neutrons, if you like, which is where you've literally squeezed out all the gaps between the electrons and the nuclei of the atoms, and what you're left with is essentially a big, extremely dense block of neutrons. And to say that it's dense would be an understatement. It's not dense in any conventional sense we would understand it. This is atomic matter that has been crushed beyond its atomic structure. So we're sort of dealing with a subatomic material star. Well, a quark star is taking that to almost another level and suggesting basically a star made of quarks. Whether these things are out there, theory says they can be, and they ought to have properties that we can detect in maybe their spectra or the way they rotate. So we ought to be able to go and look for these things. Now, whether supernova 1987A is one, I'm not sure. I think it's a bit of a stretch, but that's how these things start sometimes. So if it is, then there ought to be a predictable sign to look for, a signpost that this is a quark star, and we should be able to go and find it, and then, maybe go and find others as well. But I just think they're really cool. I don't know that I know enough about it to give you much more of a comment than that, but let's wait and see, I guess, and hope that these people can build a theory that gives us a predictable outward sign for a quark star, and then to go and find it. I believe there are theories for that, but I'm not entirely up on it, you see.
The upcoming Zooniverse project, the Milky Way project, will be asking users to find bubbles surrounding newborn stars in glimpse images from the Spitzer Space Telescope. What are these bubbles and why are they so important, and how will the study benefit astrophysics?
The Milky Way project is the project that I'm in charge of here at Oxford. It's basically sort of the Zooniverse's star formation project. We're using data from the Spitzer Space Telescope, and we're going to do a few things, but initially we're going to be looking for bubbles in the Spitzer data. Now, bubbles are sometimes created by H2 regions, which are the sort of ionized gas regions around newly formed stars. So if you imagine that the star is, if you like, sort of turned on very recently, and has started blowing away all the material that was surrounding it as it formed, and you end up with basically literally bubbles, and they look to us like rings in the data, and they're mostly circular. Sometimes they're sort of elliptical and drawn out, but we're going to be getting people to draw onto the data, literally draw those bubbles on, and so you have to sort of determine where the bubble is, how big it is, and how thick the bubble is as well. And the reason all this is important is because dust makes up a huge amount of material between stars. It's about 1% of all the material between stars, but it's incredibly important in the process of star formation, and don't understand a few things about it. And one of the things we don't understand is it seems to be able to hang around very hot young stars for a lot longer than we think it should, and so we can't quite explain that. And bubbles are a great place to look at the properties of dust, because the stuff is being swept up and pushed away, so we can understand fairly easily the properties of the stars that are within there and around that material, and then we can look at how that material is being swept up to determine its density, its physical, and that allows us to understand the dust that makes up, well, most of the stuff in the Milky Way galaxy. There's a huge amount of dust that, it's not that dust itself is making up a huge amount of the galaxy, that would be the wrong way to say it, sorry, more that it's a very important part in the formation of stars, which make up a lot of the Milky Way galaxy. So it's an important process, and it's one we're hoping lots of people are going to come and help us do. And then we have other treats in store for them when they get there. We're going to try and get you to look for star clusters, hidden galaxies. These are other things that you can see in the Spitzer data as well as the bubbles, and we hope you'll spot them along the way. So yes, launching in a few weeks. Got one or two little technical things to sort out, but then we shall be on our way.
And just as a final question, you said that you're getting members of the public involved to look at this data. If it's just drawing circles around the objects, would it not be better and faster for a computer to do it?
Well, that's a good question. It always depends with these things. So we've done a few of these citizen science projects now. It started with Galaxy Zoo, which was about visually classifying galaxy morphology. So is this galaxy a blob or is it a spiral-shaped blob? That was the very, very fundamental question. It turns out computers are only okay at doing a lot of this stuff, especially when it comes to visual identification. And a lot of the time, if you're wanting to get a feel for something in the data, then a computer is brilliant. But we find that people can provide you with a few things, and particularly crowdsourcing can provide you with a few more. Now, crowdsourcing is not the best term to use because it sort of doesn't necessarily imply a few things about what we do, but let's go with it for now. It gives you a couple of things. It gives you error correction. So 10 people telling you how big a bubble is, and well, if someone's got it wildly wrong, then you can see that straight away in the statistics. But on the whole, you'll find that those people agree, and you can take the average of their measurements. And that comes down to sort of your classic wisdom of the crowds idea, asking people to count the number of beans in a jar, and no one person might get it right, but the average of everyone's guesses won't be too far off. Crowdsourcing also gives you something that computers cannot give you, which is serendipity. So people can spot things and ask you things, and they can query what you're doing and say, hey, if you notice that this is also true, whilst I'm drawing bubbles, I'm also noticing this thing. And that's something that the Galaxy Zoo project has benefited from by the discovery of an entirely new type of galaxy, for example, and a new type of object that we didn't understand. And this sort of serendipitous discovery has become one of the cornerstones of these Zooniverse projects. Sort of trying to exploit that is something you can't do with computers. We find that people are better at some tasks than computers, and when they are better at those tasks, it is worth exploiting that to try and get the best result. And of course, that means as well that everyone gets to take part, which they seem to really like doing.
Thank you for listening to the Star Sailor podcast, Questions of a Stellar Nature Part 2, with special guest Dr. Robert Simpson, and we hope you've enjoyed the show.